All right, this is a lecture on section 1.5 of Linear Algebra by David Ley, and this is Karen Edwards commenting and making annotations based on Ley's transparencies. So 1.5 now studies a particular case of systems of equations, namely the ones where all the constant terms are equal to 0. And this is called a homogeneous system. And we're going to study some really nice pictures comparing the homogeneous systems with the non-homogeneous systems where there's actual non-zero numbers. Using the matrix equation way of writing it, get myself a good pen color here. Looks like this, now that we've learned the matrix equation. In other words, the vector on the right-hand side is just 0. That makes it a homogeneous system. And if you're looking at it the way we're used to as a system of equations, means all the constant terms on the right-hand side are 0. So we solve them the same way we always solve them, but like I said, we're going to find a nice picture that corresponds this system with what happens if these aren't zeros on the right-hand side, and how do the pictures differ. Okay, but solving this guy is the usual thing, written as a matrix equation here, and they're skipping all the process, but the process is that if you go to reduced echelon form, you just take the second row, subtract off twice the first row, and you discover that you get all zeros in this particular case. So we'll get back to that in a second. But, before even doing that, before even solving it, wait, hang on, let me erase that. I jumped again. We don't even have to solve it because we already know what a solution is without doing anything. If it's a homogeneous system, then the 0 vector is always a solution, because 0 times everything equals 0, and then you get your result. So any homogeneous system always has the trivial solution. Trivial solution means 0 equals 0 vector, is what that means. Okay. So the real question is, are there any other solutions? So in the usual, just to recap, in the usual 3 cases, our usual options are no solution, one solution, or infinitely many solutions. In a homogeneous system, you never have the no solution option. There's always 0, and then the question is there just a 0, or are there infinitely many solutions? What I mean is there just the 0 vector, or are there infinitely many solutions? Okay, so the non-zero solutions are called non-trivial solutions, so we want to know if non-trivial solutions exist. Okay, here we go. Here's the reduced echelon form, which just basically ends up eliminating the second row. So now, if we were to write this out the normal way, let me make this bigger, we would just have the single equation from the top line, 1x1 plus 10x2 equals 0. Back up in our reduced echelon form, this is a pivot position here. There's our augmenting line, which makes this silly tablet, that makes this our free variable. Which means we're going to write everything in terms of x2. That's x2. So we take this equation, we write x1 equals negative 10x2. And so our normal way of writing the solution from before would be to say that x1 equals negative 10x2, and x2 is free. So this example should lead you to see what happens in general. When are we going to get infinitely many solutions, i.e. non-trivial solutions? Well, that's when we have a free variable. Just as it was always the case, you needed a free variable to get the infinitely many solutions. So that's the same thing here. Homogeneous has non-trivial solutions, which implies infinitely many solutions. It's really saying the same thing in this case. And that's if and only if the system of equations has a free variable. So let's look at some more examples. Here's a system of equations. It's a homogeneous system because it's all zeros over here on the right. So we know that there's the zero solution, i.e. x1, x2, x3 all equal 0. Question is whether there are any non-trivial solutions. Now, without doing any echelon form, they already notice that make the claim that there's at least one free variable. Why? Because if we just look at the number of equations and the number of unknowns, we only have 2 equations. So that means we can have at most 2 pivot points. So 2 equations means 2 pivots, which means at least one free variable. So we know there will be infinitely many solutions. Now we go through and take a look at the reduced echelon form over here. I'm going to start abbreviating that REF for reduced echelon form. And which is our free variable? It looks like x2 is our free variable. Here are our pivot positions, where the leading variables are. So this is our free guy. And we could write these out. I'm going to always write the equation first so I don't get confused. 1x1 plus 2x2 equals 0. Okay, so that tells us x1 is negative 2x2. And the last line tells us that 1x3 equals 0. So then we just have x3 equals 0. It's not in terms of x2. Okay, now that should look familiar. That's what we've done before. Now we're going to come up with an entirely new way of writing this solution set. And this is based on vector notation. So now, new way to write the solution set. Sorry that the writing here is not that clear. That should be an S for solution set. There we go. So we have x1, x2, x3, and we can take these 3 guys up here. Let me just switch colors. Okay, so we look at these 3 equations, and we're going to write them down here in just a column vector format. x1 equals negative 2x2. The last equation gave us x3 equals 0. In the middle equation, instead of saying x2 is free, you could say i.e. x2 equals x2, because whatever x2 is, that's what it'll be, but it's the one you get to choose. I know that's a little strange. It'll make more sense in a second, but when you're writing it in terms of an equation, you just write it equal to itself. And then the whole point is everything is written in terms of x2. Everything is in terms of x2, which is our free variable. So we can pull out the x2 and rewrite it as x2 times the column vector negative 2, 1, 0, which is x2 times a vector. In other words, our solution set is really a vector times x2. So that is the new way. This is really the most useful way of writing it. The new way of writing it. Okay. Now, we're about to contrast this with another example, which is almost the same exact example, except it's not homogeneous. So go back up here at the top, look at the example we started with. 2x1 minus plus 4x2 minus 6x3, 4x1 plus 8x2 minus 10x3. In both cases, the equations are equal to 0. Now, there's a picture first. Ta-ha-ha. Okay, wait, hang on one second. First, we get to look at the picture of x2 times negative 2, 1, 0. So again, our solution, let's make this, okay. So remember that the solution set was x2 times the vector negative 2, 1, 0. And this is for all real numbers, x2. So in the picture, that's just all of the multiples of the vector negative 2, 1, 0. So in the picture, here's the vector negative 2, 1, 0, and all of its multiples is this entire line. So this solution set refers to this line in R3. And all of those guys will be the solutions to the system of equations equaling 0. Okay, now we move on to this corresponding other example. Aha! So if you remember the equations, it's the same things on the left, the 2, the 4, the negative 6, the 4, the 8, the negative 10, but now on the right we have 0 and 4, which means it's non-homogeneous because we're not setting everything all equal to 0. Well, when we do now we're just going to solve this, and when we do the reduced echelon form, the left-hand side should be the same as we had before. What's different is the right-hand side, we now get this 6 and this 2. So let's keep going with the process and see what it looks like. And I'm just gonna write in the equations first because I like to do that. So this first one gives me 1x1 plus 2x2 equals 6. Second row gives me x1, x3 equals 2. So now, that means if I solve for each one, x1 equals negative 2x2 plus 6. x2 just equals itself, x2, because it was free. And x3 equals 2. Now I can't pull x2 out of this anymore, like I did before, because I have that 6. So instead, I have some numbers that are multiplied by x2 plus possibly some constants that aren't multiplied by anything. So this is a slight shift from the previous situation. So along the first row, it's x2 times negative 2 and then plus 6. The second row, it's x2 times 1 plus 0. In the third row, it's x2 times 0 plus 2. And that's the same thing that is written down below. You see how this looks different from the previous solution. The previous solution only had this part of it, the x2 part. It did not have that constant vector being added on. And the x2 part of it is exactly the same because those numbers in this x2 times this vector, these numbers negative 2, 1, 0, are all based on the left-hand side of the augmented matrix. They're based on the coefficients on the left-hand side of the equation. So that's going to be the same. So this is the same as the homogeneous solution. Doesn't matter whether you're looking at my version or their version. Okay, so now let's see how this changes the picture. And they're keeping the other picture on there. So it's funny how they changed that dot. So this is the original homogeneous solution, and there was our original vector. I'm going to write it in this time, negative 2, 1, 0. And so that whole line was the homogeneous solution. Now, our non-homogeneous solution looks like the vector 6, 0, 2. Let me switch colors for this. remember it was, I'm going to write this the other way, 602 plus multiples of negative 210. Just to have it be corresponding, I'll now describe the whole line as multiples of negative 210. So this 602 plus the multiples, here's what this looks like. This vector here is the 602. Oh, I know I'm having trouble writing because I have to make this bigger. There we go. So now this vector here is the 602. And then we add to it the vector negative 2. That's really going the wrong way. I don't agree with the picture here. So I'm just, in this case, I'm going to make the picture correct. Negative 210 goes this way. So negative 210. All right. Now, the negative 210 has this x2 in front, which means we can take really any multiple that we want of negative 210. So that means we can take, but we can't change the 602. So we can take 602 plus negative 210, or 602 plus 2 times negative 210, or 602 plus 3 times negative 210, or 602 plus negative 1 times negative 210. So now our solution set is this whole line, and this is the non-homogeneous solution set. And you should notice the important relationship between the homogeneous and the non-homogeneous solution sets, which is that they are parallel. You probably already observed that. Why are they parallel? Because moving along that solution set is just multiples of the vector negative 210, and that's the same in both cases. The only difference is that the non-homogeneous solution set has this extra vector added to it first, 602, which has the effect of kind of translating the line and pushing it over into a different place in space. Just to address a side point that might have come up, you remember me telling you in a previous lecture that there was this situation we were only looking at lines and planes through the origin, and now we have a line that's not through the origin. That might seem confusing. When we were looking at lines and planes through the origin, that was the span of vectors. So in that case, when you're talking about what's the span of a set of vectors, that's when you had to go through the origin. That's not the case for solution sets. Solution sets don't have to go through the origin, as you can see here. And in fact, they only go through the origin if they're a homogeneous solution set. So that's a distinction to keep in mind. And that will always be the case. So come up with another. I'll just stick with the red pen before. So the homogeneous solution is always through the origin. And why is that? Because it always includes 0, 0, 0, which is exactly what we talked about at the beginning. 0, 0, 0 is always a solution for the homogeneous system. The non-homogeneous solution set, if it's from a non-homogeneous system, that means it's never through the origin. Because it never includes 0, 0, 0. Because if 0, 0, 0 was one of the solutions, then you'd plug it in and you would get zeros on the right-hand side. But if it's non-homogeneous, we're saying that it's not all zeros on the right-hand side, so then a set of all zeros can't possibly be a solution to give you that result. So that's another way of thinking of homogeneous solutions and non-homogeneous solutions. Homogeneous ones are always through the origin, non-homogeneous are never through the origin. Okay. Next page. This is now, and that was the highlight. That was really the main point of this whole section, is just comparing those two situations. And now as a recap, here is the, spread this apart. So I go with my previous color coding. Ax equals 0, that's homogeneous. Solution set looks like this, where it's just all multiples of a single vector. And the line will pass through 0, and then also whatever that vector is here, v is -2, 1, 0. And it will always pass through 0. And then, in contrast, ax equals b, if b is not equal to 0, it's called non-homogeneous. And then you will have this, the homogeneous part, and then the non-homogeneous part of the solution set. And that means that your line goes, so this is actually called P, and that's called V. So then your solution set goes through P and V, and it does not pass through 0. Okay. So next page, more ways of summarizing what we've already said. This is pictures, just again the parallel solution sets, where I don't know if you want me to draw this in or not, but this guy would be P, and that would be V. P is called P for particular. I think we'll get to that in a moment. And then this would be 0 and V. And so lurking behind here is some set of axes that's based at 0. So somewhere in there is the origin of the 3D coordinate system. And then theorem 6. So this makes the connection of that structure where if you are solving any system of equations, or specifically a non-homogeneous system, but this theorem applies regardless, then the point is that the solution set has this kind of structure where P is, and now we should give it the name, P is a particular solution. In our example, it was the 602. And then V sub h is the solution set to the homogeneous, which in our case was the x2 times the -201. Okay, and now we just do another example. And this example is slightly funny because they're starting you off with a system of equations, but the system of equations has only one equation, which is perfectly legitimate. You can have a system of equations with only one equation. Here it is. And they want you to describe the solution set of that equation, and then the other system is where it's equal to a non-zero number on the right. So again, this is the homogeneous, and this is going to be the non-homogeneous. Here, I'm going to stop with the color coding here. And if we start out with a homogeneous, we get the following augmented matrix. It's pretty easy to put it in reduced echelon form. We just want to stick a 1 there at the beginning, so if we divide through, we'll take 1/2 of row 1, end up with 1, -2, -2, 0. This gives us the equation x1 minus 2x2 minus 2x x3 equals 0. And now using that process that we had before, let me just give you once again, the sort of intermediate. If you were solving this in section 1.2, you would write x1 equals 2x2 plus 2x3, and x2 is free, and x3 is free. But now the way we write it is we fill in the formulas, 2x2 plus 2x3, and then x2 becomes x2, x3 becomes x3. Now, that means that this is x2 and this is x3, and now here's our vector way of writing that same solution set. So this is our new way of writing the solution set. But hang on, it's got two terms. So this is, once again, we're in the homogeneous case. And I thought the homogeneous case only had one term. It can have more than one term, but they're always going to be multiplied by a free variable. So this first part is all multiplied by x2. The second part is multiplied by x3. That's okay. What it doesn't have is it doesn't have a term that's just a constant vector by itself without a variable in front. So that's the homogeneous. Now, if we do the corresponding one that is now non-homogeneous, solve the augmented system, take half of that row, we get 1, -2, -2, 3. And the only thing I'm going to rewrite this time is this first equation, x1 minus 2x2 minus 2x3 equals 3, which means when I solve for x1, I get this guy as written, and then x2 equals that guy, and x2 equals itself, x3 equals itself. Okay, so now when we try to pull out the x2 and the x3, here's the x2, here's the x3, and now we have some constant terms, which is just 3 and 0 and 0. So that's what makes us a non-homogeneous solution set. This is the homogeneous solution set. And this, once again, is the particular solution P. And the homogeneous solution set they were calling above V sub H. So both vectors. So that's the complete solution there. I should put these all together because now that's all together. So just notice the contrast between those two with the extra constant term in the solution. And I think we're almost done. And the last thing here is just to, I wonder if I can't make this any bigger, but now we're going to look at the picture that corresponds to, here, let's take one more look before we go to the picture. So we're going to draw these two solution sets. Now, in this case, the homogeneous solution set had these two different free variables, x2 and x3. So if there's two free variables and either of them can be whatever they want, that means that our solution set is going to be two-dimensional. It's going to be a plane, because we can go in the x2 direction any way we want and the x3 direction any way we want, and then x1 is fixed as a result of x2 and x3. Okay, so we expect a plane, and here's what it looks like. This is actually two planes. Let's get this a little bigger so it's easier to see. I'll use the color coding I used originally, where I think the homogeneous solution set was red. So there's a plane here. And I'm sorry, I'm going to label this correctly, and I forgot what the numbers were. So 2, 1, 0 and 2, 0, 1. So 2, 2, 1, 0. I think that's this guy. Nope, that's this guy. 2, 1, 0. That's, I know this is a little hard to see, but this is 2, 1, 0. And this other guy here is 2, 0, 1. And that makes this red plane starting at the origin. There's the origin there. There's 0, 0, 0. So this is the homogeneous solution set. For the non-homogeneous solution set, there's this extra vector first, which is the 3, 0, 0. So here's 3, 0, 0. And then you add 2, 0, 1, or the other guy, which is sort of behind there. And now you get this other plane full of possibilities, which is the same set of vectors on the red plane, except that you added 3, 0, 0 to all of them, which that pushed that over. So you take the red plane, and you just push it 3 units to the right, and you get the green plane, which is the non-homogeneous solution set, pushed over by this particular solution here, 3, 0, 0. Okay, and that's all for now. Have fun trying some of your own.